Ladies and gentlemen, good evening. And the reason I'm clutching this physics book will become apparent in a moment, I hope. Nick England's latest book. But thank you very much indeed for inviting me to say a few words at the start of the second Noel Turner Physics Festival. And I do so feeling only partly a fraud. Let me explain. The combined science and maths teaching power of Sandown Grammar School, Welbeck College and the Royal Military Academy at Sandhurst eventually saw me with very, very modest A-levels in maths and physics, much to my amazement, I have to say. Not that I passed anything, that I got anything at all. So that is my qualification for standing in front of you, apart from being, of course, your little lieutenant. But back to Noel Turner Physics Festival, which has, as you know, two purposes. First, to celebrate the life of Noel Turner, and secondly, as his legacy, to inspire the next generation of young islanders to follow in his footsteps. Noel was an excellent role model. Having moved to the island aged 6, he attended Cowes High School and then gained a place at Merton College, Oxford, to read physics. On graduation, he joined Plessey Radar, now of course BAE Systems, in a career lasting over 30 years. His immense problem-solving skills were invaluable on his work on the Samson radar, which is now, as I'm sure you all know, installed on our Royal Naval Type 45 destroyers, that Dauntless, Daring, etc. He also used his undoubted talents in many other areas of life on the island, and was also a formidable contestant on quiz shows such as Mastermind. After Noel's death in 2015, Ellen decided to commemorate his life by arranging and sponsoring this physics festival. And thank you and everyone involved for your vision and for your enthusiasm. Tomorrow, I'm told, over 2,000 pupils will visit this college, when they will be able to hear a number of world-class keynote speakers in their fields. Students will then be able to visit a variety of stands provided by national and local companies and organisations, which shows how physics can be applied in engineering and high-tech industry. My thanks to everyone involved, particularly to Cowes Enterprise College, the new principal Rachel Kickley, and I'm sure you'll find the long-term investment in this will be very, very worthwhile. And finally, a very special thanks to Ellen Weeks for her generosity, her energy, her commitment that has made this important event possible. We very much hope that tomorrow will sow the seeds of physics into the minds of our young people, so that they might not only wish to pursue an appropriate degree in physics or some other STEM subject, but then also follow in Noel's footsteps, returning to work in and contribute to one of the island's excellent high-tech industries. Thank you very much indeed for inviting me here tonight, and I hope tomorrow is a huge, huge success. Thank you. Thank you.
We're very, very pleased to have Anu to join us. Professor Anu Ojha is from the National Space Centre in Leicester. And he's going to give us a slightly adultised version, I think, of what we're going to do for the youngsters tomorrow.
Thank you very much, John. Good evening, everyone. First of all, thank you for inviting me to be part of this festival. I'm not just saying it, but it's a real privilege to be here. You know, my background as a physicist, I spent a long time as a teacher, and now I'm pretty much a jack of all trades. I'm not very good at any of them in particular. I have very talented team members, and they're involved in a load of activities, some of them education, some of them science research, but all of it is focused around space. I've got to apologise as well, because every now and then you're going to see me look at my watch or look at that clock over there, because I'm determined not to break my time limit of just under 30 minutes, because I'm standing between you and more of those delicious canapes, you and more and your refreshments, and most importantly, you and the opportunity to see one of the rover prototypes that Airbus is building that in 3 years will be sent as the first European rover to Mars. We have one of the prototypes downstairs, and thanks to the organisation of this event, you'll have the opportunity to see that later. So what am I going to be talking about for the next 30 minutes? Well, I want to answer this deliberately provocative question. Space, so what? What have we achieved in nearly 60 years of space activity, both robotic and human? How is space ingrained into our 21st century way of lives, and in what ways are we completely dependent on it? And then I want to finish with some final personal philosophical thoughts about why science education beyond space is so critical, especially in the current era we find ourselves in, dominated by what Donald Trump calls fake news. Because critical thinking skills, that are at the heart of physics, are absolutely essential in the 21st century. But to get back to space, one of the most common questions I get asked is where does space begin? And the answer to very many people is surprising, because when you pose that question generally, the numbers that come to mind are thousands of miles or billions of light years. But actually, there are two internationally accepted boundaries of space. One is used by the whole of the world and NASA, and the other one is used by the United States Air Force and the Department of Defense. Now, the difference between these two figures is academic. The point here is that space is only 100 kilometres away. It is closer to where we are now than the distance I have come down today from Leicester. The problem is, it's 100 kilometres straight up, but if we want to get up there, we've got to battle against gravity. That's a force that's dominated the way that life's evolved on this planet for billions of years. And if we want to stay in space, we've got to deal with an environment from a radiation, from a thermal, from a pressure point of view, that's far more challenging than anything we find naturally here on the surface of the Earth. So the challenges are immense. But when we get there, the view is quite literally out of this world. This is footage from the International Space Station. So this is the sort of view that Tim Peake was enjoying during his 6-month mission on the ISS between December 2015 and June 2016. And what I love about this is that this is a living physics lesson. You can see here how Earth's magnetic field is funneling the solar wind, high-energy protons and electrons, into the polar regions where they interact with the upper atmosphere and create the aurora, the northern and the southern lights. But from a human perspective, when we look downwards, back at our planet, we can see the astonishing growth of cities as they move away from rivers and coastlines, and you can actually see countries' economic development over time spans of a decade. So this is an incredible vantage spot. And I think this is what people aspire to when they think to themselves, I want to be an astronaut. But don't get mistaken by all the hype that you see from companies like Virgin Galactic and so on. The number of people who've ever had this view would fit into one Boeing 747. It's 562. That's all that have ever had this view, because the energetic challenges are extreme. We tend to forget that when you get a view like this, you're falling around the Earth in an orbit. And the speed of the International Space Station is 18,000 miles an hour. Now, I can't picture that. But if I translate that into 5 miles a second, 30 seconds for me to get from here to Leicester, then I can start to understand, if I think of kinetic energy, that the challenges are immense. And when we look at the rockets that have been used in human spaceflight, the most famous one of all was the American Saturn V rocket that was used successfully to get to the moon on 6 landing missions and 3 others. Now, this was absolutely immense. 363 feet tall, 110 meters, metrically putting it. 3,000 tons of mass at liftoff, and more than 90% of this was fuel that was used in the first few minutes. All of this effort to get this tiny capsule to the moon and back to Earth. When you look at the energy stored in here, if this went off at once, this would be equivalent to around 1/3 of the Hiroshima bomb. So what you are trying to do to go into space is control an incredibly high-yield exothermic chemical reaction and control it in a way that it does not shake its crew or its payload to pieces. Now, when you look at images like this, I can put all of those numbers in, but what does it actually look like? Well, 3 of these Saturn V rockets were left over at the end of the Apollo program, unused. And back in 2010, when I was a bit less politically challenged than I am now, I was working at Johnson Space Center in Texas, and there's me against 5 of those F1 engines. Now what you can start to appreciate is the scale of engineering involved that we have to deal with if we're going to send humans or any robots or satellites into space. Now, I talked about us having done space stuff for 60 years. What were the drivers for us to go into space? It was good old Cold War politics. If we think back, after World War II and the carnage of what had happened in Europe and Asia, what arose from the ashes was this geopolitical struggle, the Cold War between the Soviet Union and the United States, communism against capitalism. And of course this, being in space, was the ultimate arena to show your superiority to the rest of the world. And so when the United States looked on in October 1957, they were absolutely shocked when the Soviet Union launched the world's first satellite, Sputnik 1. Now to look at it, it's not that impressive. 84 kilograms, a radio transmitter and some cadmium batteries that beeped for about 20 days. But of course, while it was beeping, it was passing over US territory every day with triumphal impunity. And the United States had a massive body blow to their pride. So the race was then on to get the first human in space. And once again, the Americans were beaten on the 12th of April 1961 when Yuri Gagarin just about completed one orbit of the Earth and landed a worldwide hero. And it was these double defeats that led Kennedy and his speechwriters to set one of the biggest challenges I think that America has undertaken. The challenge to get a human being to the moon and back within a decade. Now, the engineering was not impossible, but what was needed was a concerted national effort. And it's quite interesting that in 1964-1965, NASA was taking 5% of the US federal budget. Now, NASA's budget is about 0.5% of the federal budget. Now, I'm not saying chucking money and resources at an engineering problem is always going to solve it. But it's amazing when you have that level of funding and 400,000 talented engineers working for contractors across the country, what you can achieve. And of course, what was achieved in going to the moon was what I think are the most audacious voyages of exploration that humans have ever gone on. Because the moon is 1,000 times further away than the orbit of the International Space Station, 400,000 kilometres. And in these seminal missions between 1968 and 1972, the astronauts who went to the moon, only 24 of them, and the astronauts who walked on the moon, only 12 of them, became the only members of our species who ever explored an alien world, because that's what the moon is. The moon and the Earth is effectively a double planet system. And what I find most haunting, forget about what the conspiracy theorists say, for the engineers amongst us, they never submit any of their so-called findings to peer review because they know they're nonsensical. But what really haunts me is that these are images that were taken by American robotic spacecraft, Lunar Reconnaissance Orbiter, and you can see the footprints and the wheel tracks of the astronauts from 40 years ago when the pictures were taken, as if they were made yesterday. And these footprints will last for millions of years because there's virtually no atmosphere on the moon. We have left our mark in the universe. And in 1972, we stopped exploring like that. And many people ask, well, why? Quite simply, we changed our priorities. The Americans wanted to build a space shuttle system because they wanted to make their rockets partially reusable. The Russians started developing space stations because having lost the race to get to the moon, they wanted to see what happens if human beings in space for a month, for 3 months, for 6 months, a year. And the Russians, pardon me, I'm going to be using Russians and Soviets interchangeably, I do apologise for that, they became masters of this. But when the Cold War collapsed, with the Soviet Union's demise, we had a unique chance for cooperation, and that's what led to the International Space Station. This is pretty much what it looks like now. Has anybody actually seen an ISS pass? You know, when you look on your app, you see it go over. I chose this picture because this is when you get the most spectacular ISS passes. It's night on the ground, the sun has just set, but it's still shining onto these photovoltaic arrays. And when you see a good ISS pass, it'll be as bright as the planet Venus. And it goes across the sky, and it goes up and up and up and up and up and up and up, and suddenly goes into the Earth's shadow and disappears. Look at it with binoculars, and you can see that it is not a stellar point. You can just about make out that shape. Falling around the Earth at 5 miles a second, this was assembled over a 20-year period on more than 30 missions. And to give you an idea of scale, this is the ISS against the football field. These are the various components that have been up there. For many of these components built by
by the European Space Agency, Russia, Japan, the Brazilian Space Agency. Who have I missed out? ESA, of course, the European Space Agency. Many of these components only met for the first time when they were launched into space and travelling at 5 miles a second in Earth orbit. This is one of my favourite pictures, and we'll never get an opportunity to see this again because the space shuttle doesn't fly. If you've been on a short-haul holiday somewhere in Europe and you've flown on a Boeing 737 or an Airbus A321, that's about the size of the space shuttle orbiter. So here you get a wonderful view of how big the ISS actually is. And this is probably my favourite image from human spaceflight. This was taken on the 130th shuttle mission, SES-130, when it docked with the space station. What I love about this is we can see how the human spaceflight experience has changed. 40 years ago, in the 1960s, with one exception, Valentina Tereshkova, these would all have been male. They would all have been either American or European, Russian in origin. They all would have had piloting backgrounds. If they were scientists, they would have been trained as pilots as well, and that was pretty much it. Now, we see representatives from agencies across the world, from ethnic backgrounds across the spectrum, and from academic backgrounds ranging from your traditional test pilot and engineering to medicine.
And even in the case of Dottie Metcalf-Lindenberger, she was a high school science teacher until 2004 when she was selected as a NASA astronaut. And one of our classmates of that class, Joe Ackerman, who was also, he was actually a middle school science teacher. Right now, he is on the International Space Station in the middle of a 6-month mission, and it's his 3rd mission into space. So we've seen just how much more inclusive human spaceflight has become. And of course, we had a great opportunity when Tim Peake was selected as being a European astronaut flying for the European Space Agency. Now, many people say, well, what does an astronaut actually do up there? And I've categorised this into the order of what your priorities are. Your first thing you need to do is to keep your body healthy, because the human body is naturally lazy. If you don't use it, you lose it. And when you're in what we call microgravity, I'm not going to give you a physics lesson about free fall, okay? For any purists in the audience, you're effectively weightless. Your muscles start to atrophy away. Your bones start losing their calcium at the rate of between 1 and 1.5% per month. And so what we see here is Samantha Cristoforetti, a European astronaut, an Italian fighter pilot, exercising on a treadmill. You need to do 2 hours a day of exercise just to keep your body manageable. So firstly, keep yourself healthy. The next thing you need to do is to keep your space station healthy, because if anything goes wrong, you've got to fix it. And what you're going to see next is the least glamorous side of being an astronaut. This is a 4-hour repair job condensed into about 15 seconds. This is repairing the space toilet. And every astronaut has to do it. It breaks down with alarming regularity. It is effectively like a giant Dyson Hoover. It's only when you've done these 2 tasks that you get down to the job that you're there for, which is not taking Twitter pictures. You do that in your own time. It is to conduct scientific research on behalf of international researchers. That's what the ISS is, an international research laboratory, or a number of them. And for Tim, these are the experiments that he had to be trained up in across a range of disciplines during his 6-month mission. This is why he was doing 2 years of training. And we were incredibly fortunate, my team, when we were asked by the European Space Agency, we were given the opportunity to design one of his experiments. Now, for me, this was a fantastic opportunity. But I thought it was just going to be something like set up some procedures. But the European Space Agency said you've got 1 kilogram of payload. Now, it costs about 25,000 euros to send 1 kilogram of payload. You've got to build it, you've got to flight qualify it, you've got to train Tim up on all the procedures, because on day 67 he'll pull out his manual and he'll have 4 hours to do your experiment, and the next day he might be doing an experiment on biological research. And so we had a real challenge. And over the next year, myself, my head of teaching and learning, Andy McMurray, worked with Tim. This was taken a month before launch in Germany. We built our kit, and this was the armada of tests that we had to do for the European Space Agency before we were cleared to fly. We had to prove that when it was put onto an unmanned rocket, launched ahead of Tim, it wouldn't shake itself to pieces during launch, so he opens a bucket of bombs. We had to prove that it would not give off toxic gases during its 6-month storage period on the space station, and a whole range of other tests as well. And of course, we had to write the procedures for Tim to do. A 30-page document that was literally
breaking things down step by step. This is a scene from some of our vibration testing that we did at Harwell. What we're doing here is we're replicating the acoustic environment of
The rocket that we were using, which was a Falcon 9 rocket, one of Elon Musk's rockets, launched on SpaceX 7. We finally passed all those tests, and this is our boarding pass to get into space. This is your flight safety certificate. So there we were, 2 years of work, we had our payload sorted, and 6 months ahead of Tim, our payload was with 4 tons of other cargo on the top of CRS-7, SpaceX 7, an unmanned vehicle launching at the end of June. That was the plan. And for the first minute, everything seemed fine. Until 2.5 minutes into the mission, we had a catastrophic failure of the second stage. And I remember watching this and my heart hit the floor. Instead of going up to the ISS, our cargo and 4 tons of other cargo ended up raining down into the Atlantic Ocean. Absolutely devastated. However, in spaceflight, we've always got a plan B. We always build a backup. In fact, we built several backups, and we managed to hitch a lift within 2.5 months with another European astronaut. This was a manned mission, Andreas Mogensen, and we finally got our kit up to the space station. It was stashed away in the Columbus module, which is here, awaiting Tim's arrival. And then we had one of the most bizarre experiences I've ever had in my career, because the idea is, at some day during his mission, you will get a call saying, look, can you get to European Mission Control? You need to link up live with Tim while he's doing your experiment. And I got told at the end of January, at 4 days' notice, look, you need to get here, you need to get out to Munich, to the Columbus Control Centre. We're going to link you up with Tim, we've got 4 hours to do the experiment. The trouble was, my young son was 12 months old, and childcare issues meant there was no way I could do it. So I thought, what am I going to do? And so this is what they did. On a Friday evening, they actually linked me up live to the ISS. My little boy loved it. The mission controllers loved it because he kept trying to crawl into the screen. My wife was taking the pictures and just thinking it was hilarious. I was the only one who was having a sense of humour failure. And so I just said, look, take something away. Take it away. We cracked on. A few things went wrong. We managed to get our stuff. But what we were trying to do was we wanted to create... There's lots of experiment demos that have been done to teach physics in space. But I've always found them a bit edutainment in nature, you know, spinning bananas and stuff. We wanted to do about 50 demonstrations that students at primary school could use, but students at university could do as well. And so Tim did all of these. We've got 28 gigs of video, and I've just got a musical montage of some of the results. So what you can see here is classic demonstrations of centripetal forces, kinetic theory of gases, Newton's laws here. And we've broken all of these clips down so teachers can insert them into their lessons and so on. Conservation of momentum and collisions, behaviour of diatomic oscillators and so on. Now, you'll notice this screen at the back, and this is absolutely key, because there have been demonstrations done like this before, but we were filming in X, Y, and Z directions. What we then did with all of the footage was we used dynamic analysis software, a package called Tracker. So every single one of these experiments has been analysed dynamically, and students can actually use Tracker to take any of these and do their own analysis that will take them all the way up to first year university level. You know, it's a credit to my team who came up with the ideas here, and what we've now been offered is multiple reflight opportunities to develop the idea further still. Now, I've concentrated on human spaceflight. I've got 10 minutes left. You know, human spaceflight is what inspired me when I was younger, and I think it's what inspires so many millions of people around the world. But there is a really relevant question that gets asked. You know, what about the problems here on Earth? Why do we spend all that money up there? You know, how does space actually benefit what we're doing here on Earth? And the way I answer it is I say, look, when people ask me, what do you mean by space science? There are actually 3 categories, and only 2 of them are generally accepted by the public or known by the public. They're what I call looking out there, your astronomy, going out there, robotic and human exploration, and the 3rd category is the satellites that are looking back here. These are the satellites whose primary focus isn't out there, but it's looking back here at Earth. These are the satellites that give us the ubiquitous applications that are changing our lives every single day. And I want to take you through a few examples. You know, we've seen what's been happening in the ongoing hurricane season at the moment. This is a view of Cyclone Philin that hit the Indian coastline in 2013. We knew this was coming, how it was going to develop for a week. We knew that it was going to hit the coastline of Andhra Pradesh. The evacuation protocols were put into place, and the death toll was kept to below 100, which was still, a disaster for that region, with millions of refugees leaving the region, but the death toll was less than 100. In 1970, when a similar-sized Cyclone Bola, hit Bangladesh, the death toll was 500,000. Data from weather satellites is saving hundreds of thousands of lives every year. And it's not just using visible light that the human eye can see, we use other parts of the spectrum as well. This is the United Kingdom in what we call near-infrared, so the wavelengths are a little bit too long for the human eye to see. Now, the image has been processed, and this is from June 2003. Look at the difference that 4 months makes. June 2003, October 2003. The difference here is primarily due to loss of vegetation, trees losing their leaves, and crop management. We can actually monitor right down to individual fields the health of crops from space using near-infrared. And I think many of you will remember the discovery of the ozone hole over Antarctica. This was made by British Antarctic Survey scientists. Here you can see the ozone hole that forms every summer over Antarctica. It is nowhere near as intense as it was in the 1980s, because as soon as we discovered this, we banned the use of chlorofluorocarbons that were ripping apart atmospheric ozone when they got in the stratosphere. That never would have happened if we didn't have Earth observation satellites. And my final data set is the one that I think is the most significant when we think about climate change. It's to do with this European satellite called ENVISAT. This is like the Hubble Space Telescope of satellite applications. It's festooned with instruments looking across the electromagnetic spectrum, but all looking downwards at Earth. And the specific instrument I want to concentrate on
is this one. We're full of acronyms in the space sector. This is AATSR, the Advanced Along-Track Scanning Radiometer. Again, engineers forgive me, but in simple terms, it's like the world's most sensitive infrared thermometer or bolometer looking downwards, and as it falls around the Earth, it measures sea surface temperature. Now, there have been 3 generations of this. It's a British-built instrument, and what I'm going to show you now is 11 years of data looking at sea surface temperature that was taken by British scientists. On the left-hand side, you'll see the years. On the right-hand side, you'll see the sea surface temperature. It's visually beautiful, but it is incredibly data-rich from a scientific perspective. The first thing we notice here is we're at the same latitude as northern Canada, but we don't get their savage winters and their really, really hot summers. And of course, the reason is we've got the Gulf Stream that insulates us.
But as we change our perspective now towards Antarctica, it is incredible how you visually see the Antarctic continent almost doubling in size during its winter in June and July because of the seasonal ice. And you also see here how relatively isolated the water mixing from the Southern Ocean with the rest of the Earth's oceans actually is. Looking at Earth's oceans is critical here, because when you look at these powerhouse currents that are really driven by temperature changes, this is what powers storm systems, hurricanes and cyclones. If your water temperature is above 27 centigrade, that's when your cyclone is going to power up. And you can even see here, as we go 1997 to 1998, you can see the reversal of the ocean current in the Eastern Pacific, which is the El Nino events that we monitor. Climate change is real, have no doubt about it. The big debate is how much of this is being caused by human activity. By Earth observation satellites, we have real-time monitoring. And many of the arguments, the data set arguments that are put forward by people who are questioning the human impact on climate change, those holes are being filled very rapidly. I speak as a former questioner of climate change being caused by humans. I have to take on board from my Earth observation colleagues. The evidence is overwhelming. But I think this is the biggest challenge facing us. I was born in 1968, and back then, Earth's population was 3.5 billion. Right now, it's 7 billion, and it's growing at, 150,000 a day? In my lifetime, it's going to reach 9 billion. And the biggest challenge we have is how do we feed that population? What you can see here are the most important factors when it comes down to feeding a population, because these are the most important factors for agricultural use. How much rainfall there is, air temperature, they're the obvious ones, but what's the ratio of your precipitation to evaporation? How moist is your soil? What about the runoff water? And of course, what about your wind speeds? I show these because all of these data sets can be measured in real time from space. It's the only way to do it, and this is going to be critical if we're going to meet the most pressing challenge of our times as a species. And finally, this is the money-making side of space. You know, we now live in a world where we get almost instantaneous telecommunications. You know, events on one side of the planet have geopolitical ramification within hours, and it's only possible because this network of telecommunication satellites orbiting the Earth around the equator. You know, it's not just Sky TV, it's the news coverage and so on. And of course, you know, how many of us have got, so I put it down over here, how many of us have got a smartphone and without even thinking about it, we're using its navigational capabilities? You know, we are relying on the time signals from GPS satellites, and they're not just used in so many different apps, they are used to timestamp every single international bank transaction. You turn off this electronic architecture of satellites looking inwards, global economy will grind to a halt in about 72 hours. That's how dependent we are on these services from space.
And this is the money generator, because these are the revenues that are generated by the global space sector, and the 2016 figures are about 280. That's not $280 million a year, that's $280 billion a year. The space sector makes far more money than we spend on it from government. And in the UK, we are a world leader in all of those areas of space science. Nearly 40,000 employees. The figure that gets me for any economists is about 14% of our gross national product is dependent on services from space. And so it's a great opportunity for the next generation of scientists and engineers. I'm down to 3 minutes left. I'm determined not to bust my time limit. So I just want to finish with some final thoughts. And there's one activity that you all need to do, and you must promise to indulge me with this, because it's going to seem a little bit odd. Before I get to it, though, personal perspectives. I said that it was human spaceflight that I fell in love with when I was a kid. Actually, it was astronomy and robotic exploration, but specifically astronomy. 1973, I remember getting a book on astronomy when I was a kid, and this was the best telescopic view we had of the planet Saturn in 1973. Back then, it was the only planet that we knew had rings. It had 9, maybe 10 moons. There was a controversy about a moon called Janus. And we knew that one of its moons, Titan, was about the size of Mercury and had a thin methane atmosphere. Now, if you would have told me back then that in my lifetime I would see a NASA European mission, this is Cassini, launching on a 7-year voyage to get to Saturn, and having a more than 10-year orbital survey of Saturn, I would have said this is science fiction. You know, we have now seen, because of Cassini, which ended its mission back in September, many of you will remember, we have seen views of Saturn that are completely impossible to obtain from Earth. You're looking down Saturn's polar vortex here. We've seen these incredible views of the rings being edged on here, but the shadows being curved. And this is Titan, Saturn's largest moon in close-up detail. You can see Saturn lurking here behind the rings. Titan lurking there. If Titan was on its own in the solar system, not orbiting Saturn, we'd call it a planet and we'd be going there like this. The thing that's special about Titan, though, is that we sent a European spacecraft into its atmosphere. And what we found with Cassini is that Titan is a world that's got lakes, it's got rivers. This is sunlight glinting off a titanium lake. And as we descended through the atmosphere with the Huygens lander in 2005, on the 14th of January, you can start to see what look like river systems here. And the most distant landing anywhere in the solar system wasn't achieved by NASA, it was achieved by a European mission, and this was actually a British instrument that made this touchdown. Now you might be thinking, why is he getting so excited about rivers and rain and lakes? I mean, we have that on Earth. This is a world at minus 180 degrees centigrade. These are not lakes and rivers and rain of water. This is methane. And so we've got a truly alien landscape that in my lifetime we've seen explored. And of course, other missions have shown us worlds of fire. Io, one of Jupiter's largest moons, the most volcanic moon in the solar system. We've seen worlds of ice. And this, I think, is really rewriting the textbooks right now. Instead of this is this tiny moon of Saturn that's not even the size of the United Kingdom. Until 2005, it was the most boring place anywhere. Until suddenly, when Cassini was flying by, we saw these astonishing geysers of salt water erupting from its insides. It's got a saltwater ocean, and more recently we flew through these plumes and we found organic molecules. So in the space of the last 12 years, this has gone from being one of the most boring places in the solar system to the most likely place to find life anywhere. It's amazing how you can just rewrite your discoveries even within a few years, and these are great opportunities for the next generation of people. But my final thoughts
our big picture, and they're to do with the Hubble Space Telescope, everyone's favourite telescope. It's been up there since 1990, and I want to share with you some of my almost favourite Hubble images. Hubble has rewritten the textbooks on astronomy, on physics, in so many different ways. It's a NASA telescope the size of a bus with a lot of European involvement, and here are some of my almost favourite images. Look at this. This is M16, the Eagle Nebula. This is a region of cloud and dust in which new stars are being formed. So 5 billion years ago, our solar system formed out of a cloud of dust and gas just like this, about the size of a pixel on this image. We have seen the birth of stars with Hubble, and we've also seen the death of stars. This is what happens at the end of a star like our Sun, at the end of its life. This is NGC 6543, it's also called the Cat's Eye Nebula, and at the end of its life, in 5 billion years, our Sun will puff off its outer layers to form a planetary nebula. But Hubble has also shown us huge collections of stars. These are galaxies. This is M51, the Whirlpool Galaxy, a vast collection of 150 billion stars like our Sun, and it's so far away the light has taken 29 million years to get here. This is another one of my almost favourite Hubble images, M104, the Sombrero Hat Galaxy, a spiral galaxy seen edge on. Again, about 100 billion stars and about 30 million light years from the Earth. Those are my almost favourite Hubble images, but I now want to show you the most significant image ever taken in science. Before I do that, though, what I want you to do is to imagine that you're doing this. And if you've got a pen, I want you to do it. I want you, on your thumbnail, to imagine drawing, or actually draw, a 1 millimetre by 1 millimetre square. This is great because you're actually pretending to do it. There is a mathematical reason for why I'm asking you to do this, and I will do it as well. Now, what I want you to do then is when you've got your imaginary or real 1 millimetre by 1 millimetre square, I want you to point it out up to the sky. For this to work mathematically, this should be 1 metre from your eye. And the mathematicians will already be thinking to themselves, well, 1 millimetre by 1 millimetre at 1 metre, what angle of arc am I subtending? It's about 1/20th of a degree. What we are doing is what Hubble did in the early 2000s. Hubble looked at a blank section of sky in the constellation of Fornax that was the size of a 1 millimetre by 1 millimetre square when it's 1 metre from your eye, about 1/20th of a degree of arc. And this was an empty section of sky. And Hubble looked at it over 840 orbits, collecting more and more photons, seeing fainter and fainter objects. And what emerged was the most incredible image in science. I'm really hyping this up. And this is... Now, I can see that some of you being very polite. I can see a look of disappointment in some of your faces. When you look back at the drama of this, and the beauty of this, what's so special about this? Well, what emerged in the Hubble Ultra Deep Field image was $10,000. But when you look closer, these dots are not stars. Each one of these dots is a galaxy containing 100,000 million stars or more. Now, I don't know what's more amazing. The fact that Hubble saw 10,000 galaxies, each with 100,000 million stars, in a tiny fraction of sky like this, or the fact that I can use GCSE or A-level maths to approximate the number of stars in the universe. I'm not going to do this with you today. I do it with sixth formers. It's about imagining an imaginary sphere around yourselves, 4 pi r squared surface area, blah, blah, blah. This is the number that you get. 1.2 times 10 to the 23. And that is probably an underestimate. There are more stars in the universe than grains of sand on all the beaches of planet Earth. And we're going to discover more. And so space science has transformed our perspective, not only of how we are affecting our own planet, but where we are in the universe. Final views to share with you. I talked about Cassini. What I love about this is space science has given us perspectives that are unique. This is Saturn eclipsing the Sun. You can never get this view from Earth because Earth's closer to the Sun. But what you see is a faint blue dot. You are all on this picture. This is Earth seen from beyond Saturn. By space science, we get a new perspective of where we are in the universe. And so I want to leave you with the thoughts of Dave Scott. He was commander of the 4th successful lunar landing, Apollo 15. They landed the most beautiful landing site, Hagley-Ackerman. And this is what he said. He said, while I'm standing here today, I'm reminded of a fundamental truth. Humanity must explore, and this is exploration at its greatest. Now, for a long time, these are his words as he set foot on the lunar surface at the beginning of 3 days on the surface. I thought he was talking about space exploration, but I now think He was talking about the journey of civilizational exploration and development that we have been able to do through harnessing science, mathematics, engineering, medicine. You know, our societal progress has only been possible because we've had generations who've been willing and disciplined to learn science, to apply engineering in a variety of different fields. And this is why, you know, for me to be able to, and members of my team, support initiatives like this and specifically support this festival, it is a real privilege. Why I also think it is so important in terms of science education is I sit down on some government panels and we talk about science education and the importance of economic return, blah, 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 and I'm sure we've all been in there filling in the documents and we do it, but there's something much more powerful than this. And I talked about it at the beginning. Science and physics in particular develops those critical thinking skills. And why they are so important now is that we are living in a world that is effectively an ocean of information when you look at what is on the internet. And this is an ocean of information that is getting deeper every day, it is getting more turbulent every day, and the only tools that young people and us have to navigate that ocean is those critical thinking skills that are at the core of what we do in physics and engineering and mathematics. And actually, for me, that is far more important than any economic return to UK PLC. I hope there's no government here. I stood up and I said this to ministers before. That's why science education is so important. And so I think for our young people, if we are supporting them in science education, we've got to give them as many opportunities to see not only how it links with the world of opportunity they will have, which is why it's so great to see so many employers, both here tonight and representing the festival, but also to make them realise that they are empowering themselves in a way that is going to be even more important as we move on into the future. Ladies and gentlemen, thank you very much. If you've got any questions, I'll be delighted to take them, but I am aware that Bruno is waiting for you. No, Bridget is waiting for you. It's Bridget today. And you also have your canapes and drinks. So thank you very much, everyone.